So we're farther than this, right? A little bit.
We're on compliance.
Right. Okay. All right. Video on. This is the third lecture overall in 233. Third lecture on the chapter on respiratory system. Let me just review one thing real quickly because I know several of you are confused about this, and that is this business about the bronchial circulation. First of all, you need to realize that 99% of the blood coming back to the body, which is unoxygenated, comes to the right side of the heart. Remember, it either comes down through the superior vena cava or comes up through the inferior vena cava, and it goes into the right atrium, goes to the right ventricle, goes out through the pulmonary artery. The pulmonary artery splits into a right and left pulmonary artery, and all of that blood percolates through the lung tissue, through the alveoli, through the little capillaries, and it gets oxygenated. And then all of that blood reaccumulates back into the pulmonary veins. Now they're called, pulmonary veins that are going back to the heart, because that's what veins do. Veins go to the heart, arteries go away from the heart, but this is the only set of veins in the body that are super oxygenated, right? They're bright red blood because they just came from the lungs. They're going back to the left side of the heart this time, to the left atrium. They're going to go through the left ventricle, they're going to go out through the aorta, and they're going to go to all of the body, okay? And it's going to carry oxygenated blood to all of the body in order to supply oxygen to every cell in your body, including your finger. We always talk about the finger because that's where blood has to go to not only take oxygen to your finger, but to bring the waste products back from it. Okay, that's the way 99% of the blood goes. However, there is another system, which is a very small system. It's called the bronchial system, and that's because the tubes that are inside the lungs themselves, they have thickness to them, they have cartilage in them, they have muscle in them. They can't just absorb oxygen from the alveoli because they aren't near any alveoli. They are in the tubes that are going through the lung. Those are the bronchial tubes, right? They need their own supply of oxygenated blood, and they get a set of arteries after it came off the aorta, comes off some of the intercostals, comes off the brachiocephalic, and it sends blood to the bronchial tubes. Okay? Now you would think, since it's systemic blood in the systemic system from the aorta basically, it would go back to the vena cava, but it doesn't. That would be kind of a redundant system to carry such a tiny bit of blood. So instead of doing that, it just dumps it straight into the veins, the veins that are going back to the heart, that are bright and oxygenated, but they're still low pressure, right? And those are so that lowers the overall oxygen content of the blood going back to the heart from a PO2 of 100 to a PO2 of about 95. Why? Because the oxygen has been sucked out of that blood as it went through those bronchial tubes and supplied oxygen to the muscles, to the cartilage, to the different layers of the bronchial tubes. Okay? Kind of weird. Don't mean to confuse you with that. It's a very small system, but it does make a little bit of difference in the PO2 of blood going back to the heart. So otherwise, it would be 100, a PO2 of 100%. Yeah?
It dumps into the pulmonary veins.
Dumps into the pulmonary veins, that's correct. Going back to the left side of the heart. Excuse
So my friend actually just asked me a question. She's in another one of the A&P classes. Why does the PO2 of arterial blood differ from that of air? Excuse me.
From alveolar air?
Yes.
The first number was?
The PO2 of arterial blood.
Arterial blood is usually 95, and that's because there's a little bit of this mixed in bronchial blood that's brought it down a little bit. In the alveolus, it should be 100.
Okay.
And it should fill completely up. Even though that blood passes through those alveoli and through those capillaries in just a matter of a few seconds, it still becomes 100% saturated almost all the time. Okay? Okay. If that doesn't make sense, please call me or talk to me in lab, and I'll try to explain it with some models over there maybe. Compliance is an important term. We talk about the compliance of your lungs. In other words, how flexible are your lungs? How easy is it for them to expand? How easy is it for them to compress? Now, the way we really started learning about this was trying to ventilate people on a ventilator. If they were sick, and if they had a little pulmonary edema, or if they had some COPD or stuff, you found out that it took an awful lot of pressure from the ventilator to blow up their lungs. And they're always hooked up to a pressure monitor, and you can just sit there and watch it. It might go up to 30 millimeters to blow up the lungs if somebody had sick lungs and if they were pretty sick. But that meant they had a very low compliance. It didn't stretch easily. It didn't take the oxygen easily. That's really all compliance is. It's kind of a relative number, but I hope that's what it means. If you just think compliance is the opposite of stiffness. Compliance means it's softer, it's compliant. Stiffness means they're stiff. It takes more pressure to open and close. Okay? Low compliance requires greater force. When people start getting sick, their compliance goes down, and it's harder and harder for them to breathe. And if you watch somebody that has pneumonia try to breathe, you know, they're sucking in everything in. They're just trying hard to get air in and out. The factors that affect compliance, part of it is just the connective tissue. As you get older, just from getting old, you develop a more stiffness in your chest wall. Your ribs don't move as well. The muscles, your cartilages, everything moves a little slower and a little tougher. The other thing that matters with compliance is the level of surfactant. If you don't have enough surfactant, especially in those newborn babies we talked about the other day, they used to take amazing amounts of pressure to blow their lungs up if they weren't compliant because they didn't have the surfactant. Yes?
So let's say you're sick and you have a low compliance. Can your body counteract that and produce more surfactant to increase your compliance?
Yeah, usually the surfactant is not a problem, except for little babies. Although when you get really, really sick, then maybe you're not making enough surfactant. But that's pretty unusual. Okay? Yeah?
Is that what they're checking for when people have pneumonia and you have to breathe into that little plastic and breathe as hard as you can? Is that what they're checking for? You know what I'm talking about? The little plastic things?
Spirometer thing.
Spirometer, where you blow really hard into it?
Let's talk about that when we get over to,
Okay.
Was that before surgery?
No, after. Like my mom had a collapsed lung and she always had to.
Gotcha. Yeah, I'll talk about that. I have one over there. Okay. Normally, it takes very little pressure difference to expand your lungs. In other words, breathing regularly, breathing slowly, and I try to inspire, take a breath in, regular breath. I can usually breathe with just 1 or 2 millimeters of mercury change. And how do we create that negative suction? Basically, you can think of it, the way we breathe is we suck air in. The way we suck air in is that we lower the pressure in our chest. Well, how do we lower the pressure in our chest? We do that by increasing the volume in our chest. You remember? Volume and pressure are inversely related. Boyle's law. So if you can increase the size of your chest cavity, that will lower the pressure, and assuming your trachea is open, down will come air. And indeed, in quiet breathing, it only takes 1 or 2 millimeters of mercury in order to do that. We suck it in, and then we just relax, and out it goes. Okay? The muscles that are used to inspire the air are the external intercostals that go this way, remember, and the diaphragm. When you're asleep at night, basically you breathe with just your diaphragm. All right, normal atmospheric pressure is 760 millimeters of mercury. That's on a normal day at sea level, at a certain temperature, I think. But anyway, that's 760 is the conversion factor. We'll talk about millimeters of mercury quite a lot in this class. The intrapulmonary pressure, so we're talking about atmospheric pressure, that's outside, and intrapulmonary pressure is if you could put a little monitor into one of the alveoli in your chest, okay, and see what the pressure is there. If you can lower that pressure just 2 millimeters, you're going to suck air in and take a breath in regular breathing. So in relaxed breathing, the difference between the atmospheric pressure outside and the intrapulmonary pressure inside is very small, only about -1 millimeter on inhalation and maybe +1 millimeter on exhalation. So it does not take much effort and pressure change in order to breathe air in and breathe air out. The maximum pulmonary pressure, what's the most intrapulmonary pressure you can generate? Well, you've probably seen these weightlifters and they go, yeah! And they're straining to lift a weight, but at the same time they're also generating very, very high pressures inside their chest. And if you're a weightlifting instructor, you probably tell your students, always expire when you're really straining. So you're expiring. Why? Because you just want to keep your trachea open and not hold that high pressure back. You don't want to generate this high of pressure because it's quite a lot, up to 100 millimeters of mercury. Yeah?
So when we get to really, really high end deadlifts and we're trying to pull a PR, we'll actually hold our breaths through the concentric action, so as we're actually pulling,
Yeah.
and you'll drop instead of doing it, just because the extra pressure inside your chest will help keep your back and your spine straight.
Oh, absolutely. Weightlifting to that degree is not a normal event. Yeah. One other pressure we need to think about is what's called the intrapleural pressure. Now, where do you think the intrapleural pressure is? What?
In between the two parts.
In the pleural space, yeah, between the visceral pleura and the parietal pleura on the outside. Now, clearly, it's not even a real space. It's just a little potential space with a few drops of fluid in there to keep it all slickered up, right? But we've figured out you can put a little catheter in there and measure the pressure. And here's the things you need to know about intrapleural pressure. It's always, always, always negative. Okay? It normally averages about -4. Now, why does it need to always be negative? Think about it. Why would you need your intrapleural pressure to always be negative?
Because you want the lungs to remain open.
Because, well, you want your lungs to stay right up against your chest wall, right? And so as you increase that volume and try to suck in, you need that intrapleural pressure to basically suck your lung out with the chest wall, right? So indeed, the intrapleural pressure always stays negative, about -4. It can go up to a high of -18. And the point being is that it always remains lower than the atmospheric pressure throughout the respiratory cycle. It's always more negative.
What would cause it to get greater? If the average is
Pneumothorax, right?
If you're sucking in really super hard, I guess. Yeah. And just this is a unrelated issue, but this is mentioned in your book, I believe. We have lots of ways of measuring pressure. If you go check the air in your tires, it's measured on pounds per square inch on most bicycle pumps. Normal atmospheric pressure for a scientific study is usually about 760 at sea level. Another unit is called torr, T-O-R-R, and torr are the same as a millimeter of mercury. So 760 torr is the same as 760 millimeters of mercury. Pounds per square inch, a lot of times you'll go to look at cylinders, gas cylinders, and they're stamped on there in so many pounds per square inch. Normal atmospheric pressure here would be about 15. That's pretty normal level. And one more is that Dave Zaleski, when he reads the weather report every morning, he says the barometric pressure is 29.76 and rising. What the hell does that mean?
It's measuring mercury.
In what?
Inches.
Inches. That's inches of mercury. Okay? So I'm always amazed that our weather reports always come in that unit, inches of mercury. So 29.75, I think, is about, that's inches of mercury. And sea level pressure is normally 29.9. So 29.9 inches of mercury is the same as 760 millimeters of mercury. So please don't become confused by all of these different units. In this class, we will only use millimeters of mercury. 760 is normal atmospheric. Takes about a millimeter to suck in and blow out of difference and so forth. All right, respiratory cycle. I always make this point, and that is, you know, I've told you that the pressure in the pulmonary circuit is pretty low, right? Now blood is coming back from your arms and your legs coming up to the end of the vena cava, and it's going into the chest. And you wonder what pumps it, because there's hardly any pressure left from when it got pumped out of your heart. You know, the pressure's gotten down to about 2 millimeters. It's trying to work your way up, and you need your muscle, the muscle working around your veins and your legs to help pump that blood up. And you've got those little flapper valves that kind of in the venous system, remember, that open and close. And but you also got to remember that when you suck in, you're lowering the pressure in your chest, and not only is air coming into your chest, but you're sucking blood into your chest. You're sucking it out of your arms and your legs because you're lowering the pressure in your chest, and you're making it easier for all that blood to flow back to your chest and thus flow back to your heart. Does that make sense? You got it? You got that look on your face like... Okay. A couple of terms you need to know. We're going to do a lab on pulmonary ventilations today. The tidal volume is a term you need to understand. Tidal volume is very simple. Think of it as the tide. It's the number of cc's of air that go in and out in a normal, quiet breath. A couple of injuries to the chest we can talk about here real quick. A pneumothorax is anything that causes air to pour into the pleural space. Okay, so you may have heard of a pneumothorax referred to as a collapsed lung. If you get air in your pleural space, then there's nothing to suck that lung up and hold it up against the chest wall, and so the lung collapses. That's called a pneumothorax. If you got blood in there, it'd be called a hemothorax. If you got a lot of water in there or serum, you'd call it a hydrothorax. Yeah?
And so if you have a pneumothorax, then the intrapleural pressure will become positive, correct?
It'll basically become zero.
Okay.
But it means that negative.
Or a little bit positive, but you have no more negative to suck your lung up with. That's the problem. Another thing is atelectasis. This is another form of a collapsed lung, really. But atelectasis means that the lung tissue itself has collapsed, and you can't reopen up all those alveoli. A lot of times atelectasis is caused by pneumonia. The other thing that atelectasis is really caused by is by pain. If you have surgery, you're talking about your mom after surgery, they're trying to get her to breathe on that machine. What that's about is trying to force you into taking a deep breath to re-expand your lung and keep from developing areas of atelectasis. I'll tell you my atelectasis story when we go over there. Okay, so let's look at some of these pressure changes as we go through this respiratory cycle thing. So here's a lung sitting there at nice normal rest. Notice that the diaphragm is in its normal shape when you're not breathing in. Lungs, alveoli, a whole bit up there. Notice this is the intrapulmonary pressure that you're recording on this chart. And notice that it's going from a low of -1 millimeter to a high of +1 millimeter. That's how little air, a little change in the pressure it takes to fill your lungs up with a normal respiratory cycle. The intrapleural pressure, if you had a monitor out here in the pleural space, you notice that it starts off at about -2.5, it goes down to about -6. The point being that it is always negative. Doesn't matter whether you're inspiring or whether you're expiring. In normal breathing, your intrapleural pressure is always negative. And finally, this is your tidal volume. This is the amount of air that's going in, and this is the amount of air that's going out. Okay, so 500 cc's came in, 500 cc's came out. That's a normal resting breath. Make sense? All right, now how do we breathe? Well, I've already told you that the diaphragm and the external intercostals are the main ones for quiet breathing. External intercostals, remember, they go this way, and they go from the rib on top to the rib on the bottom. They lift the ribs up. As you lift the ribs up, it opens up the chest and sucks the air in. Okay. Now, that's for quiet breathing. Those two muscles are for quiet breathing, and you notice there are no muscles to blow it out. It just goes out on its own. Okay? Now we're going to talk about heavier breathing. And to do we need to recruit some other muscles. And we recruit these accessory respiratory muscles, is what we call them. And when activated, these can increase the amount of respiration a lot. Deep breath, okay? I didn't do that just with my diaphragm and just with my external intercostals. I recruited some new muscles. I've already said this. Inhalation is always active. Inhalation is passive in slow breathing, but active in fast breathing. Most of the air that we move in and out is about 75% of it is caused by the contraction of the diaphragm. The diaphragm goes from this position. When it contracts, it pulls down. That sucks air in. When the diaphragm relaxes, the diaphragm goes up and air goes out. The accessory muscles, however, that help you in this process are the sternocleidomastoid. Remember it right here. It's going to lift up on your sternum and lift up on your clavicles to make more room. The serratus anterior, remember that one? You might look at it on a picture. Pectoralis minor, and the scalene muscles. The scalene muscles come from up here in your neck, and they basically pull the ribs up as well. Here they are. Here's the sternocleidomastoid up here. These are the scalene muscles up here. Here's the serratus anterior, remember back there. And I think the transversus thoracis, which wasn't on that last picture, on the last slide, but here it is. So those are all the accessory muscles that help you breathe deeper. Yeah?
When you sigh, do you activate the accessory muscles, or is that still just your intercostal?
I suspect you recruit some accessory muscles. Yeah. Now, if we're going to actively exercise, and we're going to be taking these great deep breaths, we're going to have to blow it out. We can't wait on it to just work its way out. You actually push it out. So we have these muscles of active exhalation, which are the internal intercostals. Remember, if the externals pull the ribs up, the internals pull them back down. Okay, so that helps push the air out. Transversus thoracis goes across your ribs. I said that wrong on the last slide. And then your abdominal muscles. So, you know, if you want to build up big abs, just try breathing out really hard, and you can feel your abdominal muscles here contract. And indeed, you know, your rectus abdominis, your transversus abdominis, your internal your internal and your external abdominal oblique muscles, all of those tend to help you blow out when you're exercising. There you have the rectus muscle and all the other abdominals. Other abdominal muscles are not shown here. Internal intercostals pulls it back down, and the transverse thoracic muscle pulls the ribs down as well. So that's the deal. Here's the relisting of the inhalation ones, but you need to keep those muscles in mind. So we have different patterns of breathing. I've kind of been illustrating two of them, and I think that's the main things for you to keep in mind is quiet breathing and very active breathing. Active breathing, maybe. Quiet breathing is referred to as eupnea. I have never, ever in my life, ever heard that word used, although it's in this book. It's on this set of slides, but I think that's a silly word. Now, apnea, you guys know apnea, that means no breathing. I just never heard this one used. It's normal breathing, anyway. Costal breathing. Well, diaphragmatic breathing is dominated by the diaphragm, but it's not ever acting totally by itself. And then costal breathing is really shallow. That's just using your rib cage a little bit. Most of our exhalation happens by basically just elastic rebound of the chest and returns the alveoli, the lungs, everything back to its normal position. Forced breathing is called hyperpnea, another word I've never heard used before. But obviously, if you're exercising, you're going to be doing that. You're going to use all of your accessory muscles to both help you inspire and to help you expire. And at maximum levels, you're going to get exhausted. That fair to say? Or you're going to pass out from hyperventilation. We'll talk about that also. Okay, so the respiratory rate and volume is quite adaptable for you. We don't ever think about whether we're breathing enough unless we can't breathe, right? Now, if you go underwater and hold your breath, you'll find pretty quick that you don't feel good. In fact, let's just do a little experiment here. I want everybody to take a deep breath in and hold it. Now, kind of wiggle a hand at me if you start feeling crummy. Already. Keep holding your breath if you can. And is everybody feeling somewhat weird? You know what's wrong and why you're okay, breathe. You know why you're feeling weird? You know what the chemical change is that's going on in your blood when you do that? What's happening to the carbon dioxide? It's building up. You are building up carbon dioxide in your body, and what's that do? Carbon dioxide is acidic, right? So that's making your pH go down, and you are becoming acidotic, okay? But just within 30 seconds there, you can drop your pH to 730 from 740, which is normal. Your pH varies very quickly with breathing. As a result, it's really pretty important that we always breathe. Yeah?
I know that one of the biggest long-term damage for holding your breath or asphyxiation over a long time is going to be brain damage, right?
Yeah.
Are there any long-term side effects via the pH rising?
No. The reason you're going to get brain damage is not because of the pH, it's because you don't have enough oxygen. So at first, all you're feeling, everybody here, nobody passed out or felt dizzy probably or wasn't getting enough oxygen to their brain. They were just building up PCO2. And I make that point because you need to know that PCO2, the level of carbon dioxide in your blood, is the main determinant of your breathing, of how much you breathe. Not a low oxygen level. Now, a low oxygen level can hurt you and it will cause brain damage. Here's my story on that. In '79, I was going to go out on the aircraft carrier. In order to go out on the aircraft carrier, I wanted to be able to fly in the jets off the aircraft carrier. And to do that, I had to get what was called water survival skills and back seat, and how to release your ejection seat training, it was called. So you'd sit there in the seat and they'd say, okay, eject, and you'd reach up and you could grab a thing here and pull it down, or if you're here between your legs, there was another, you'd pull it up. And when it did, it shot you up to the top of the building. It's an explosive charge that blows pilots out of the plane in jets. You've seen the ejection seats fire in time.
Top Gun.
Yeah.
Well, Top Gun, there you go. Goose got hit in the head. It's a terrible thing.
Poor goose.
Poor Goose. I know.
Man had it rough the whole movie.
Oh, I know. Anyway, but then they did another thing with us, and they took us all and they said, there was about 20 of us there that day, and they said, okay, now we're all going to go into this decompression chamber. And I think I was the highest ranking person in the room, so they said, okay, doctor, here's a deck of cards, and we're going to have you deal the cards, and each time you deal a card, you read the card and announce it. Ace of spades, queen of clubs, 7 of hearts. And it was that quick because what they were doing was sucking all the oxygen out of the room so that there was no oxygen. We could breathe all we wanted to, right? We could maintain our pH, our PCO2 just fine, but when there's no oxygen to breathe, you lose consciousness. Now there's a terrible story about that. You remember the golfer that always wore the knickers, whose name was, I'll think of it in a second. He won the U.S. Open a few years ago, and then he was with 5 or 6 other guys, and they were flying in a little jet. They were going up to, from down south in Florida somewhere up north, somewhere to another golf tournament. And they were flying, and suddenly nobody could reach them on the radio. And so finally they launched a fighter jet up, and they went right along with them, and they noticed that both of the pilots were unconscious and were out of it. And everyone on the plane was dead from lack of oxygen. And it eventually ran out of fuel and crashed into a field somewhere up in Iowa or something. But
Payne Stewart?
Yeah.
Payne Stewart, thank you. Isn't that Google wonderful? Yeah,
It's a
Payne
golfer
Stewart.
who died in plane.
There you go.
Done.
All right. So yeah, so you got to have oxygen, but you got to do the ventilation thing. Ventilation is what we're talking about when we're talking moving air in and out. Okay. Our respiratory minute volume, you can probably figure that's the amount that you breathe every minute. And the way you figure that is you figure out what the tidal volume is. In other words, how much are you breathing in and out with each breath? Multiply that by the number of breaths per minute that you take. And that gives you a number for pulmonary ventilation. Now, how many times a minute do you breathe?
12.
16, yeah.
Okay.